Hello and welcome to Cognito Key. Today we're diving deep into a piece of tech that honestly keeps our digital world from completely falling apart. It's called the sliding window protocol. And trust me, it's the unsung hero that makes sure all our data gets where it's going, safe and sound.
Have you ever really thought about it? When you're watching a movie online, what's stopping the server from just blasting your phone with the entire 2-hour film all at once? How does anything online stay orderly instead of just becoming a huge mess of data?
Well, the basic problem is pretty simple. You've got a sender that can shoot out data way faster than a receiver can catch it. It's like trying to catch 100 tennis balls fired from a machine all at once. Your device, it has a little buffer. Think of it like a small bucket. If data comes in too fast, that bucket overflows, and poof, packets are lost. And that's the chaos we need to prevent.
And this is where our hero comes in, the sliding window protocol. The best way to picture it, think of it as a super efficient traffic cop for the internet, making sure all the data flows smoothly without causing a massive digital traffic jam.
So what is it really? The sliding window protocol is basically a master multitasker. It does two critical jobs at the same time. First, it handles flow control, which is all about managing the speed. Second, it takes care of error control, making sure everything arrives perfectly. The real magic, though, is that it lets the sender send a whole bunch of data packets at once, without waiting for an "okay, I got it" after every single one. That's what makes it so fast.
The secret is right there in the name, the window. Okay? Imagine a mail sorter who decides they can only handle, say, 10 letters at a time. That group of 10 is their window. They simply won't accept an 11th letter until they've processed and made space. That's pretty much exactly how this protocol works.
And it gets a little more detailed, because this isn't just a one-way thing. You see, both the sender and the receiver have their own window. The sending window is the number of packets the sender's allowed to send without getting a thumbs up. And the receiving window, that's the receiver's available buffer space for those packets. For everything to work, these two windows have to be in perfect sync.
Now, this protocol isn't just a single thing. It actually comes in a couple of popular flavors, each with its own way of dealing with mistakes. So let's check out the showdown, Go-Back N versus Selective Repeat.
To really see the difference, let's create a classic problem. Let's say the sender is sending out a stream of packets, but one of them gets lost along the way. How does each of these methods fix it? First up, let's see how Go-Back N handles this situation.
Okay, so sender sends packets 0, 1, 2, and 3. Uh-oh, packet 2 is lost. The receiver gets packet 3, but it's confused. It was expecting packet 2, so it just throws packet 3 away. Meanwhile, the sender is waiting for a confirmation for packet 2, which never comes. Its timer runs out, and it knows something is wrong. Now here's the key part. Go-Back N goes back and resends everything from the lost packet onwards. That means it resends packet 2, packet 3, and anything else that was in the window.
Kind of feels like using a sledgehammer to crack a nut, right? It works, but it's not very subtle. So let's run that exact same scenario again, but this time with the more sophisticated selective repeat protocol.
The setup is exactly the same. Packets 0, 1, 2, and 3 are sent, and again, packet 2 gets lost. But watch this. When the receiver gets packet 3, it notices 2 is missing. But it doesn't discard 3. Nope, it holds on to it, putting it in a buffer. Then, when the sender's timer for packet 2 runs out, it resends, you guessed it, only the single lost packet, number 2. So much more precise.
And this table just lays it all out perfectly. It really shows the trade-off, doesn't it? Go-Back N is way simpler. The receiver doesn't have to be very smart, but it can waste a ton of bandwidth resending data that was already received just fine. Selective Repeat, on the other hand, is super efficient with bandwidth, but it's also more complex. The receiver needs more memory and more logic that handle those out-of-order packets.
So, why are we talking about all this? Why does it matter? Because this protocol is quite literally one of the foundational pillars of our modern digital world. It's what makes communication over the internet not just fast, but reliable.
The advantages are massive. You can send a whole stream of packets at once. You get that perfect balance of speed and accuracy, and it even unlocks cool stuff like full duplex communication, where data can flow both ways at the same time. All of this adds up to a much smarter, much more efficient internet for all of us.
The big idea behind its efficiency is something called pipelining, and this quote explains it beautifully. Instead of the old, slow method of send one, wait for an OK, send the next, pipelining just fills the entire data pipe. This creates a constant, nonstop flow, which is exactly what makes our connections feel so fast. So,
The next time you're streaming a movie and it plays perfectly without a single glitch, you can give a little nod to the invisible traffic cop making it all happen. It really makes you wonder, right? What would our internet even be like without it? My guess is a slow, frustrating, and totally chaotic mess. Thank you so much for joining us for this explainer here on Cognito Key. If you found this useful, please give this video a like, share it with someone who might be interested, and of course, subscribe for more deep dives into the technology that shapes our world. We'll see you in the next one.